In last lecture, we have discussed three inequality. That is Markov inequality, Chebyshev inequality, and also Jensen inequality. In the last section, 4.6, we will discuss other inequality. To have a simple expression for the formula, so we introduce a new symbol like this. Okay, first of all, we write this norm xp to represent this the p roots of ex power p. So this is the notation. We call it the p norm of x. So in this case, whereas this one is known as the p norm of x. Okay, next, we're going to use these notations here. As you can see, this p norm is equals to the expectation value for x power p and then the p root. So it depends on whether this is infinities or not. Okay, so we're going to use this notation. So we write x belongs to LP to means the p norm of x will be less than infinity. If we use back our standard notation, so this one just simply means E of the modulus of x power p will be less than infinity. By introducing this symbol p norm, so we can express the following four inequality in a relatively nicer form for it. First, we have this so-called the order inequality. So in this case, we have two parameters here, p and q, which have to fulfill this property. 1 over p plus 1 over q is equals to 1. Okay, if x belongs to LP, so which means the expectation of x power p is not infinity, and y belongs to LQ, so that means using this symbol, then we have the first norm of xy is less or equals to the p norm of x multiplied the q norm of y. So this is the more general one, we so-called the Holder inequality. Okay, next, if we taking p equals to q equals to half, we obtain more simple inequality, so-called the Cauchy-Schwarz inequality or Cauchy inequality. So in this case, this is actually a special case for our Holder inequality. That is, we just simply taking p to be half and q to be half. Okay, so then we obtain Cauchy inequality. This is one. So in our course, so this will be the most important one. So we're going to use this more frequently. Next, we have this so-called the Napier inequality. When x belongs to LS and any r less or equals to s, so the r norm for x will be less or equals to s norm for x. And finally, we have this so-called the Minkowski inequality. Whenever xy belongs to LP, then we have this inequality. So if you have learned this in your calculus, so you can see a special case for this will be so-called the triangular inequality. Okay, so triangular inequality is a special case. For this Minkowski inequality. Okay, as I said, in our course, the most important inequality among these four will be the Cauchy-Schwarz inequality. So I think it will be better I will express this inequality in terms of the expectation value, which seems to be more comfortable to you guys. Okay. So here's the notation. Okay, so this is the Cauchy. I simply call Cauchy inequality or Cauchy-Schwarz inequality. So that is the first norm of xy. So this is less or equals to the second norm of x multiplied the second norm of x multiplied the second norm of y. So if you want to use back the standard notations, then this will become, so this will be first norm will be e of xy. Okay, so supposed to be power of 1 here. Okay, maybe so if this is power of 1, so actually we do not need to consider it. Yeah, so that's why we can just simply look at e of modulus of xy. So this will be less or equals to, okay, so this second one will be e of x power 2, and this is 2, then we have to take another power of half. So likewise, we're going to have e of y power of 2, and then we have to take power of half. So this is what we so-called the Cauchy inequality in the form of our expectation value. So I think so we can express this in terms of square root or square. Alternately, you may express it like this, in this way, or you may express this e of xy less or equals to square root of ex multiplying ex squared and ey squared. Alternately, you may express this in this form. You may square both sides to animating the square root. So it turns out to be e of modulus of xy squared less or equals to e of x squared multiplying e of y squared. So you may either take the first form or the second form. Either this or this. Okay, so we shall look at some example which regarding to this Cauchy-Schwarz inequality. Okay, so let's look at the first examples here. Okay, example 1. So if x belongs to L1, if x belongs to L2, then x belongs to L1. Okay, before solving this, just recall our definitions here. So what's the meaning of x belongs to LP? So that's the meaning. X belongs to LP just simply means the P norm of x is not infinity. So if you are not comfortable with this symbol, so you may retreat back to the notation of expectation value. So that is just simply means that the P norm of x is not infinity, which is equivalent to say that the expectation value for modulus of xp is not infinity. right? So if you are using this notation, so we can translate this example or the statement for this example into this form. So which is that is, if e of modulus of x squared is not infinity, then e of modulus of x. Okay, here we are supposed to have a modulus here, and since we are taking squares, we can actually remove the modulus. Okay. So we don't have to consider the modulus. So we can translate this sentence by using the notation of expectation value. That is, if e of x squared is not infinity, then e of modulus of x is also not infinity. So we can actually solve this problem by using the Cauchy-Schwarz inequality. So again, just recall the Cauchy-Schwarz inequality. So for Cauchy-Schwarz inequality, there is, if you have x in L2, that means maybe we can take x in L2, y in L2, that is, okay, maybe I will just state the inequality, that is e of modulus of x modulus y, okay, always less or equals to square root of e of x squared multiply e of y squared. So this is our Cauchy-Schwarz inequality, provided these two are finite. And also, we can refer back to our theorems 4.1.3. Okay, so in this theorem, we have this e of the indicator function 1a is just the probability of a. So if we putting a to be epsilon, sorry, not epsilon, if we putting a to be the sample space omega, then we're going to have e of 1 will be equals to 1. Okay, because p of omega must be equals to 1. Okay, so now we can apply these two results to solve these examples. So let's look at the solutions for that. Okay, what we can do is we can take y to be 1 in the Cauchy-Schwarz inequality. Okay. So first we have to recall our hypothesis. Given that from the hypothesis e of x squared is not infinity. So this is just simply means that x belongs to L2. Okay. So this is not infinity. So by taking at y equals to 1 in Cauchy-Schwarz inequality here, so what can we have? We're going to have e of modulus of x will be less or equals to square root of e of x squared multiplying e of 1. After taking y to be 1 here. So then, like I said, e of 1 must be equal to 1. So this is less or equals to square root of e of x squared here. And because of this is less than infinity, so this one will be less than infinity. And so you can see that e of modulus of x will be less than infinity. So this is just simply means that x will be belongs to L1. Yeah, so this is how we can apply this Cauchy-Schwarz inequality to prove this simple statement. That is, if e of x squared is not infinity, then E of modulus of x will not be infinity. So this is the first example to applying the Cauchy-Schwarz inequality in solving some problem. Okay, next we look at one question from our tutorial 4. So there is question 10. So let's copy the questions. So this is tutorial 4, question 10. So I believe you should have seen this before, so-called the correlation of two random variables, x and y. So which is defined as this E of x minus mu x multiplied y multiplied and so on. So here mu x is the mean for x, mu y will be the mean for y. Likewise, sigma x will be the standard deviation for x, and sigma y will be the standard deviation for y. So we want to show that the correlation of x and y, modulus of correlation of x and y is always less or equals to 1. In other words, we want to show this, right? Modulus of E of E of x minus mu x, y minus mu y, divided by square of gradient of x multiplying. Okay, maybe we can bring this over there. So in other words, we just need to show this is less or equals to sigma x multiply sigma y will be the standard deviation for x and standard deviation for y respectively. So this is less than the gradients of this. All right. Okay, this is okay. Okay, by the definitions of gradients of x and y, so we can express this like this: E of x minus mu x, y minus mu y, less or equals to square of E of x minus mu x square, then E of y minus mu y squared. Okay, so this is what we want to prove. Okay, so let's go back to our Cauchy-Schwarz inequality. And because in the original statement of our Cauchy-Schwarz inequality using x and y, so it's a little bit confusing here. Let's restate the Cauchy-Schwarz inequality in other symbol. Okay. So let's say by replacing x and y with u and v, so it becomes like this: E of modulus of u v will be less or equals to E of u square, E of v square. Right, so now I think it's quite clear already. So what we need to do is, let's say by changing the color here, I think you will get the picture clearly. Okay. So let's say we are replacing this with a red color. So this would be x minus mu x squared. So that means we're going to have this. U squared. Okay, there's no square here. So this is So after changing the color for this two symbol, I think you should have a better idea how are we going to apply the Cauchy-Schwarz inequality to solve the problem. Okay. So this is the statement that or the inequality that we want to prove. So that is actually looks like the form of this Cauchy-Schwarz inequality. So the only problem is there is no modulus over here. Okay. So to do this, we just need to recall back another theorems. Okay. So just to recall back, so first, this is a Cauchy-Schwarz inequality. Next, we also know this. In fact, I think this is quite natural. You guys should know this. So the modulus of E of any random variable, so will be always less or equals to E of the modulus of this. So this is theorem 4.3.2. Okay, I think by applying all this idea, so I think using this theorem and this Cauchy-Schwarz inequality, so we should able to get this expression. Once we able to get this expression, you can easily get back to this result. Okay. Okay. To make it easy, so let's say this is our Cauchy-Schwarz inequality equation 1 here. So solutions here. Okay, what we can do is substituting u equals to x. Okay, maybe minus mu x and v equals to y minus mu y in Cauchy-Schwarz inequality 1. So then we can have this. E of modulus of x minus mu x multiply y minus mu y, okay, less or equals to E of modulus of x minus mu x square E of y minus modulus of mu y square, and then we have a square root here. And according to the definitions, so these two will be the variance for x and variance for y respectively. So we're going to have this will be less or equals to square root of variance of x multiply variance of y. By use back our notations, so this is just sigma x and sigma y. So according to here, so then this is what we can have. E of modulus of x, maybe we can say this. E of modulus of x minus mu x multiplying y minus mu y will be less than this. So this is one equation here. And we know this according to our theorems. We know this. E of x minus mu x, y minus mu y will be always less or equal to this. So like I said, this is just simply by theorem 4.3.2. So this is statement 3. So by using statement 2 and statement 3, so we're going to have this E of x minus mu x y minus mu y less or equals to sigma x and sigma y. Sorry, I think this we have a modulus over here according to these theorems. So this will be less than this. So by putting this over here, then we got it. Hence, the modulus of correlation of x and y, which is just equals to the modulus of E of x minus mu x, y minus mu y over sigma x, sigma y. So this is always less than 1. Okay, so here's are two examples how to use the Cauchy-Schwarz inequality to solve certain problems here.